I'm very glad to introduce today's speaker, Sarah Millholland, from MIT. So welcome back, Sarah. Sarah was a second fellow here in Princeton for 3 years or 2 years?
Yeah.
2 years. 2 years with Josh Wynn. And Sarah was a PhD student originally at UC Santa Cruz, and then transferred to Yale. And after her postdoc, she joined MIT as assistant professor. So Sarah is an expert in exoplanets. She worked a lot on the demographics, formation, and evolution of planetary systems using data-driven dynamics. So Sarah, today we'll talk about tidal sculpting of short period exoplanets.
Great. Yeah, thank you for the introduction. It's great to be here with you all today. And feel free to ask questions throughout the talk. I'm really excited to tell you about some of the things that my group are working on the formation and dynamics of exoplanets. In particular, I'm going to highlight these very short period, very scorching hot exoplanets that are now known to be very abundant across the galaxy. So I think still kind of one of the most defining discoveries across the field of exoplanets is just the sheer diversity that we see in this space of planet size versus orbital period for known transiting planets. We can see that planets populate almost this entire space. Even kind of regions that they don't populate, like down here, are areas where it's currently still really hard to detect planets. So there's probably planets filling that space too. We just haven't been able to see those yet. But it's clear that the planet formation process is capable of producing a very huge range of outcomes. And in particular, if I overlay a line indicating the 88-day orbital period of Mercury, we can see that there's many, many known exoplanets that orbit much closer to their stars than Mercury does to our own sun. We also can see a couple of different classes of planets here. There's a really large number of these very close in planets in between the sizes of Earth and Neptune, with orbital periods ranging from days to months. And in fact, about half of sun-like stars are accompanied by these small planets. So really the ubiquity of this class of planets and the fact that we don't see this size regime or orbital period regime in our own solar system has motivated a lot of studies across the community to understand what these planets even are and how they form and evolve. These small planets are frequently found in very tightly spaced multi-planet systems, which we kind of know now as the compact multi-planet systems or compact multis. So for instance, here's a few examples of these compact multis, all with around 4 or 5 planets all squashed into a very tight region of the system. And a really cool discovery that came through the field in the last few years is that in contrast to kind of the diversity of the planet sample as a whole, these compact multi-planet systems display a very striking degree of uniformity. They show very kind of orderly structures with very kind of uniform spacing in this log period. And they also show similarly sized planets within a given system, with maybe a bit of size ordering as well. We can see this another way with this depiction here, which is a collection of the planetary systems with 4 or more planets discovered by the Kepler mission, although many more of these have been discovered by the TESS mission as well. But if we kind of look through each line being a different planetary system, I'm sorry, it's kind of it's not as jerky on my own screen, but you can see that planets tend to be more similar in size to their neighbors than you would expect if systems were just kind of assembled randomly from planets across the population. We now collectively refer to these patterns as the peas in a pod patterns due to the kind of visual similarity between these planetary systems and a collection of peas in a pod. So yeah, that's a bit about these compact multis, but we also see larger planets in short period orbits too. There's planets anywhere between, Neptune size to super Jupiter size as well. These tend to not be in these compact multi-systems, and they tend to have lower observed multiplicity, sometimes containing distant giant planets, which kind of are indicated with these lines connecting off the screen here. But these don't display that kind of nicely uniform structure that the compact multis do. Another thing that these often show is that their orbits of the planets can be misaligned with respect to the directions of their host stars' spin. So this angle here between the stellar spin vector and the planetary orbital angular momentum vector is called the stellar obliquity, and it's going to come up a little bit later during this talk. Okay, so if we look at this short period planet population, we see there's a lot of interesting complexity. There's a lot of very unusual orbital architectures and interesting systems that we think must be understood to some degree from dynamical sculpting. And by that, I mean evolution of the systems largely after the initial formation in the disk. And these things can include things like resonance interactions between planets, tidal interactions between planets and their stars, radiation-driven effects from the host stars, or things like giant impacts and collisions. And so in one of the kind of main overarching themes of my group is to try to study these dynamical processes in an effort to explain some of the interesting features that we see in the planet population. And by doing that, try to constrain the physics of planet formation and evolution. So we're working on all kinds of dynamical sculpting, including all the things in this list, but today I really want to focus on tidal interactions and how they are responsible for sculpting features of the short period planet population. All right, so many of you probably already know this, but when short period planets are, when a planet is in very close proximity to its host star, both of these bodies experience a tidal deformation. And if the planet's orbit has a non-zero eccentricity, or if the planet has a spin axis tilt, then this tidal deformation of the planet will vary in time in sort of this stretching and squeezing way, which leads to interior friction and heat deposition in the planet. So this is called planetary tides, and these will generally dominate the orbital evolution if they're present, and they cause the planet's orbit to circularize and decay inwards. But if a planet reaches a state where it ends up on a circular orbit with a synchronized spin and zero axial tilt, then planetary tides no longer dominate, but you still have further tidal evolution due to the deformation in the star. So in kind of the traditional equilibrium picture of tides, when the stellar rotation period is slower than the planet's orbital period, as is usually the case for these short period systems, then the tidal bulge of the star will lag behind. And this creates a torque that transfers angular momentum from the planet's orbit to the star, causing the planet's orbit to decay and the star to spin up. So the magnitude of this effect depends on the planet's proximity and its mass, so it's strongest for very close-in massive planets. So for the first part of the talk, though, I'm going to focus on these planetary tides. And again, these are due to distortion in the planet, and they cause this interior heat deposition or tidal heating in the planets. To understand this a little bit better, I always like to bring up this example of the kind of most miraculous or marvelous case of tidal heating in our own solar system, which is Io, the closest Galilean moon around Jupiter. And Io has this extreme volcanism. It's so geologically active because of the tidal heating that it experiences. And it has this because it's in a resonance with neighboring moons that keep it forced at a non-zero eccentricity. And this elliptical orbit means that when it's closer to Jupiter, that it's more tidally deformed than when it's further away. And this constant stretching and squeezing leads to all this tidal heating.
Sorry, why the resonance make it eccentric?
Yeah, so it's in a mean motion resonant chain with the other Galilean satellites. And mean motion resonance is force eccentricities due to the like torques that you get from the periapse passages and the conjunctions between planets.
So the resonance is pushing the eccentricity up and the tidal is dissipating.
Yeah, the eccentricity is in a balance between the resonant forcing that would increase the eccentricity and the tidal decay, which would cause the eccentricity to jam.
So for the Soviet planet, I mean the satellites.
Yeah.
Satellites, they're mostly in resonance except one, right? Does that cause any other problem or?
So yeah, Callisto is not part of the resonant chain. I think the dynamics are mostly forced by the resonances, but I don't think Callisto has much like effect on it. That's a good question. Yeah, so the kind of the theme of this talk is that these tides play a really critical role in sculpting aspects of the short period planet population. And they allow us to understand some planetary features that we might not have otherwise been able to. There's a lot of examples of this beyond what we're working on in my group, but today I want to focus on a few examples of things that we've been excited about. So one being the formation of hot Jupiters via high eccentricity migration, hot Jupiter orbital decay, and the formation of Neptunes on polar orbits. So yeah, the first topic I want to talk about is the formation of hot Jupiters. These hot Jupiters are very, very close in gas giant planets that orbit on circular orbits with orbital periods of just a few days. The existence of these is one of the oldest puzzles in exoplanets. In fact, the first ever discovered exoplanet around a main sequence star was a hot Jupiter, 51 Pegasi b, which this discovery being so groundbreaking that it won Didier Queloz and Michel Mayor a Nobel Prize in 2019. So the existence of these gas giant planets is mysterious because the prevailing wisdom in the field is that the hot Jupiters are in orbits that are too close to their stars to have form where they're currently found, because the materials and conditions necessary for planet formation to build a gas giant don't exist in that regime. So how did they form? Well, one of the kind of dominant theories for how they formed was that they started out in much more distant orbits, maybe beyond the ice line, and that they obtained very eccentric orbits due to perturbations with another star or planet in the system. So once the orbit is very eccentric, on its periapse passages, the planet passes very close to the star. And I was just talking about how extreme eccentricities, or not even necessarily extreme, but eccentric orbits cause this tidal dissipation and can cause the orbits to change. And so over time, this dissipation caused the orbits to shrink, and it can eventually leave the hot Jupiter on a very tight circular orbit. So if this theory is correct, though, you would expect that we would sometimes find very eccentric giant planets that are on their way towards becoming hot Jupiters. One such planet was discovered way back in 2001. This is HV 80606b, which is a giant planet with a super eccentric orbit of 0.93. It's undergoing tidal circularization and will eventually become a hot Jupiter. But in the last 20 years since this planet discovery, there were no kind of analogous hot Jupiters that had been found, which has caused some tension with high eccentricity migration as a theory for hot Jupiter formation. So recently, our group was involved in the discovery of another one of these hot Jupiter progenitors. This work was led by postdoc Arvind Gupta. And so they first detected this planet in test data. Here's just a single transit of this planet. And when they followed it up with radial velocity data from a variety of instruments, they found that the orbit was very, very eccentric. You can tell that by this spike here, which is the periapse passage of the planet. And modeling all of this together, they found that this planet is around 5 times the mass of Jupiter with an orbital period of 165 days and an eccentricity of 0.94, so even larger than HB 80606b. Arvind also found that the system possesses a distant binary star companion at around 1,000 AU. So as part of this discovery, we showed that this planet is still indeed undergoing high eccentricity migration and is on its way to becoming a hot Jupiter. And MIT undergraduate Tatum Im and I worked to perform dynamical simulations of the planet's history. So given this distant binary star in the system, we showed that the planet was subject to these oscillations on multiple Kozai-Lidov mechanisms, which cause these extreme oscillations in the planet's eccentricity and inclination. And so this data here, or this simulation here, is showing 1 minus the eccentricity, the inclination of the planet's orbit, and the planet's semi-major axis and periapse distance. So in this kind of example simulation, we start out the planet at around 10 AU, so quite a bit further from the star. And this binary star causes these extreme oscillations in the eccentricity. And when it reaches these very high eccentricity passages, it dissipates energy and the orbit slowly shrinks. So this red line corresponds to where the planet is today. So it's just fallen out of its Kozai oscillations. You can see that in the top eccentricity picture there. But it's still eccentric and is now just kind of slowly circularizing down. Yeah.
Did you have to make an assumption about the orientation of that outer binary, or is that measured and constrained somehow?
Yeah. So unfortunately, we don't have great constraints on the binary parameters. It's just like a projected separation. So, but we showed as part of this that in order for this to work, the binary would have needed to start nearly polar, which is kind of a little bit concerning. It's like
how like within a few degrees?
Yeah, like 88 or above. Yeah. So maybe that's okay. But I mean, also we don't know the true semi-major axis of the binary. So its A and E could be a lot different than the fiducial values we assume.
So how far is the binary companion?
Like it's around 1,500 AU. Yeah.
So I noticed that your initial eccentricity doesn't seem to be 0. What motivated the choice? 1 minus E is that right? Or maybe it's just very, very close to the early time.
You mean like
Top left corner of the
Yeah.
first panel, right?
That's a good question. We did start the planet near like
Near circle.
near circular. It might just be kind of cut off.
Yeah, it might just be really.
Yeah,
narrow.
really close to that. Yeah.
I see.
Yeah. Yeah, so another piece of evidence that this planet has undergone a history of these Kozai-Lidov oscillations is that they were able to measure the projected stellar obliquity. So the observations showed that the planet's orbital angular momentum vector is oriented nearly the opposite to the stellar spin vector. So it's on a retrograde orbit. And it's kind of hard to get something like that without something like Kozai oscillations. So this is an important discovery because it provides really compelling kind of direct evidence for the high eccentricity migration pathway. It kind of shows that like this has to happen in at least some fraction of hot Jupiter formation. But I think that it brings up an interesting question then of why are these kinds of systems so rare? HB 80606 and this planet are only 2. I mean, there are some other fairly highly eccentric giant planets, but nowhere near this regime. And so if this really is a dominant formation pathway for these systems, shouldn't we have found more of these by now? So one way that this might be reconciled, there's something important to consider here, is that the planets might move quicker than expected through the high eccentricity phase. And this might be the case if tidal dissipation is even more efficient than we might think otherwise. So there's indeed an expectation for this in that planets that reach very, very eccentric orbits can be subject to these very highly dissipative dynamical tides through the excitation of oscillation modes or waves through the planet. So instead of the kind of tidal model that we assumed in the simulation that I just showed, where there's just an equilibrium static tidal bulge on the planet, these tides are time-dependent oscillatory modes that can lead to much more complex and highly more efficient dissipation. So this was kind of previously offered as a solution for why we might not see as many of these highly eccentric hot Jupiter progenitors. And so with this new planet discovery, there's kind of another opportunity to look at this. So I'm working with MIT undergraduate student DJ Libo, who's currently exploring whether this new planet that was just found could be consistent with dynamical tides. And I'm not going to show too much results from that today, but kind of the preliminary thing we're finding is that it actually might have been kind of hard for this system to be consistent with dynamical tides. I can talk more about that if you're interested. But regardless, I think this is an interesting thing to try to explore, not only whether this example case study could be consistent with this formation pathway, but whether dynamical tides could help explain the lack of these highly eccentric progenitors that we've seen so far. So yeah, it's an ongoing study that hopefully I can talk more about another time. Okay, so everything that I've talked about until now has just been how do we form hot Jupiters? But and in this process, I talked about the role of dissipation inside the planet. But once the hot Jupiter reaches a circular orbit, it can still undergo further tidal evolution. And it turns out that their orbits continue to decay slowly, and they will do this as a result of stellar tides. There are some interesting insights that we can get from this, which I'm going to discuss more. And this work is a project that I've done with Morgan McLeod at CFA and Felicia Zhao, an undergrad at MIT. So yeah, once the hot Jupiters reach their final orbits, they're circular now, and so planetary tides are no longer important, but we still have this interaction with the star that causes their orbits to decay. Hot Jupiters and other close-in planets are experiencing this decay, and there's a lot of observational evidence for this, including both individual systems and at the population level. So for instance, there's some evidence from individual systems, the most solid of which is JWST. Observers have measured the repeated transits of this planet and have found that the transits are speeding up very slightly, decreasing, so they're coming faster at a rate of around 30 milliseconds per year, meaning that this planet has only just a few million years left of its life before it's going to crash into its star. There's also another cool example from Kishila and co-authors where they detected an infrared transient that appeared to indicate the exact moment that a planet was engulfed by its star, which could have been as a result of this tidal in spiral. Beyond individual systems, there's also evidence from the population level. So for instance, Hammer and Schlafman in 2019 studied the galactic velocity dispersion of host stars of hot Jupiters, shown the average of the hot Jupiter hosts is shown with this orange line here. And they compared that to a matched control sample of field stars, and that's shown with this blue histogram. So the velocity dispersion is a proxy for age since it increases over time. And so they found that the hot Jupiter host stars are significantly kinematically colder and thus younger than field stars. So this was also supported by recent work from Miyazaki and Suda, who showed that the occurrence rate of hot Jupiters goes down as a function of age. So both of these population level trends are consistent with the picture where hot Jupiters are slowly destroyed by tides as their host stars are still on the main sequence. But despite all of this evidence that tides are acting in these systems, we still don't actually know what the dominant tidal mechanism is or what its efficiency is. By the word mechanism, I am talking about the exact physical manner in which the dissipation is, in which the tidal energy is dissipated inside the star. And as I've already kind of alluded to for giant planets, there's two kind of components of the tide. There's the equilibrium tide or dynamical tides, the wave-like dissipation, and we don't know which of these dominates. So also with efficiency, we typically parameterize this in terms of the stellar tidal quality factor, Q, with smaller values of Q indicating more efficient dissipation. And we don't know what the magnitude of this Q is or whether it has a dependence with the tidal frequency. So this is something that we were interested in trying to get a better handle on in this work. So our approach to doing this was to look at a population level distribution of something that I'm going to define as the decay timescale. So first, let me define the instantaneous orbital decay rate tau A, which depends on various properties of the system, including the star's tidal quality factor. This tau A is a measure of the decay rate at a snapshot in time, but I'm going to define the decay timescale as the time that it takes for the planet to move from its current orbit to disruption by the star. So this is the amount of its lifetime that the planet has left. We can compute this in terms of tau A if we make a parameterized form for the tidal quality factor of the star. So if we assume that this goes as some Q naught times P to the alpha, where alpha, if alpha was 0, this would be what we call a constant Q model. Then if we assume that parameterized form, then the decay timescale is related to tau A with this relation here. Okay, so to explore what can be gained by studying the decay timescale distribution, we constructed first a toy model of the hot Jupiter population. So here we're randomly sampling system properties, including planet and star masses and radii, semi-major axes, the ages of the stars, and so on. And for what I'm going to show on this slide here, we're just assuming a constant Q model, but I'm going to relax that later on. So we let this population evolve over time and then plot the decay timescale distribution at different ages of the universe. So here, for instance, is what this distribution looked like when the universe was 8 billion years old, 9, 10, and so on. And so a couple of interesting features pop out of this. We see first that this distribution looks like kind of a broken power law form, where this part at lower decay timescales looks to be in an approximate steady state. And this is kind of interesting because an individual planet would be born with some decay timescale. And then as it ages, it would move through time down to smaller decay timescales. But despite that kind of flux through of individual planets, the distribution as a whole is in an approximate steady state. We can also see that there's some kind of break location beyond which the distribution is not in a steady state.
So the statistics,
Go ahead.
So the statistics are sketchy enough, right? I don't think you can actually tell at the sort of 2 to 3 counts per bin, whether it's steady state or not.
Yeah.
If you repeated this with just many more samples, you can actually.
Yeah, that's a good point. I mean, these are histograms for sure with binning issues and so on, but we did show in the paper that this is really well described by a continuity equation model, and that this region is pretty well consistent with being in a steady state.
Okay, so the slope doesn't change in time, but you can still see it shifting over.
Yeah, there is a small amount of this there. Josh, did you?
Yeah, can you tell us more about the assumptions about the formation of them? What, are they randomly distributed in orbital distance and time?
Yeah, so for this, what's shown on the slide, it's a uniform semi-major axis distribution from, I think, like 0.01 to 0.1 AU. But in the paper, we do all sorts of, we try all different things and show that it's not super sensitive to that. And it's just a constant star formation rate. So planets pop up, they move through time, and then they get destroyed and will, they'll leave after they're destroyed, or if the star is destroyed, then they'll also, like, before they get decayed, then they will also leave the distribution. Yeah, this is a pretty simple picture, but in the paper, we look at different semi-major axis distributions, which we would think would be the most kind of important thing for sculpting this, and we don't find that it changes this slope of the steady state region too much, actually.
So that's basically because the migration, the high energy migration mechanism would not produce very closing things, right? So you assume the closing things there just from the tidal migration.
Yeah,
So then you change the initial condition, it doesn't matter how you change the initial condition, because anyway, this steady state channel is filled just by the.
yeah, essentially the steady state region is mostly sculpted by the decay of the existing population rather than how planets are initially born in semi-major axis space. And there is complications of, like, if planets form through high eccentricity migration, then they are first undergoing this long period of planetary tides. But we can sort of think about this as, like, where is the semi-major axis that the planet is planted with after it has circularized, after it's finished high eccentricity migration? Where is it then planted? And then this decay happens after that.
And how small separation is it when the time scale is 1 gigawatts?
I think around 5 days or so, orbital period-ish. I mean, it depends on planet properties and so. So when we notice that this pops up, we realize that this gives us a really interesting opportunity to probe the properties of tidal dissipation. And that is because this steady state region is sensitive to Q naught and alpha, specifically the break location, which is it's not a super clean break, but roughly where this is sensitive to this Q naught. And the slope of the steady state region is sensitive to this alpha. So this picture here has all just been simulated data, but our goal with this study was to look at the decay timescale distribution of the observed planet sample, and then try to look at the properties of the steady state region there to try to constrain this alpha and Q naught. So I'm gonna kind of skip the details of how we actually do that. I'm happy to talk more about that if you're interested, but just reporting here are findings that we constrain this alpha to be in this range of around -4 to -2, and Q naught from 10 to the 5.5 to 10 to the 7. So the fact that this alpha is in this range tells us that Q has a steep frequency dependence. Q is not independent of the period of planet. And here you can see what these distributions look like for the observed planet sample when we use alpha equal to -3 and Q naught equal to 10 to the 6, just for kind of plotting purposes. These different lines are just like bootstrapping the planet sample, but we can see the steady state region here in this sample of including all stars or just those around cool stars. The result that we get here is in really strong agreement with the prior study by Penna et al. In 2018, who presented constraints on the stellar tidal quality factor. And I think the agreement here is really remarkable because they used a completely independent method. Josh was on that work, and it also involved measuring the spin up of the planet's host stars and using that as a means to constrain Q. But in this study, they found alpha around -3 and Q naught equal to 10 to the 6, which is in good agreement with what we find as well. So the big thing that you can do with this study then is look at the theoretical implications for these tidal mechanisms. We can look at our results in this space of Q versus the tidal period, which is about half the orbital period when the stellar rotation period is long. So our constraints here are shown in this gray region, where I'm really only plotting within the range of orbital periods that we have good constraining power on. And here is the empirical result from Penna et al. Overlaid, showing this really strong agreement between these two empirically based methods. But now we can look at the implications or the kind of predictions from theory. So I'm going to overlay on here a bunch of different theoretical predictions and then kind of step back and look at what seems most favored. First, we can look at the equilibrium tide predictions, so equilibrium tides are the large scale quasi-hydrostatic deformation response of the star. This represents the low frequency response to tidal forcing. And this is thought to be dissipated due to its interaction with turbulent convection. And there's different prescriptions for what's the effective viscosity of that dissipation. And that gives rise to these different lines here, with probably the most trusted, the one that comes actually from a simulation being that the long dash and the dot line there. So next we can look at predictions from dynamical tides, which are these internal waves excited by tidal forcing that propagate through the star. So there's different modes of dynamical tides. In convective zones, there are so-called inertial waves, which are restored by the Coriolis force. So these have a complicated frequency dependence in general. It's kind of like a forest of resonances. So it's very common to just make a kind of frequency average kind of predict or response there. But these inertial waves only propagate in regions for which the tidal period is greater than half the stellar rotation period. And that's generally kind of not overlapping with this regime for hot Jupiter systems. Another mode of dynamical tides are these internal gravity waves, which are only supported in radiation zones, and these are restored by buoyancy. So in stars that have thick convective envelopes, internal gravity waves are excited at the radiative convective boundary, and they propagate inwards through the radiative zone to the center of the star, where the amplitudes of those waves may increase due to like gravitational focusing, and those waves can break. So it becomes kind of a traveling wave into the interior of the star. But this predicts a dependence with a steep slope in the opposite direction. So looking so far, these mechanisms don't agree particularly well with what we find, but there's one last mechanism that is kind of out there, this being resonance locking. So here we're still talking about gravity waves, but with resonance locking, the planet can become trapped in a resonance with with the stars and one of its natural oscillation modes. And this can allow for a very large amount of dissipation and fast orbital migration. So Ma and Fuller in 2021 predicted a resonance locking line that looks something like this purple line here, which kind of taking this at face value, this appears to agree very well with our empirically based constraints. That equilibrium tides, inertial waves, and internal gravity waves don't appear to do very well, at least if acting in isolation. But this resonance locking agrees really well, suggesting that if these constraints are in Q are correct, then this could be strong evidence for this resonance locking mechanism.
What is it resonant with? Which modes in the star is it resonant with?
Yeah, so the star has like a full dense spectrum of these oscillation modes. And then the planet has is creating some tidal frequency. And so it's because the star's spectrum of frequencies is so dense, it's very likely that there's going to be one that's nearby. And as the star, so it just is an overlap between those two, which can then just drive a very strong response inside the star. But the thing is then as the star evolves, those frequencies change just due to the slight, structural changes of the star. And so this can effectively push the planet to keep on that resonance and move the planet in to keep that lock.
So as the planet is moving in, its period is changing, and as the star is evolving, these resonant frequencies also change. So you're saying that they're changing synchronously, sort of, so that the resonance is always maintained while separations happen.
Yeah, the planet moves so as to maintain the resonant lock.
But these are not internal gravity waves or any of the other waves that you mentioned, the inertial waves. So these are different waves.
They are gravity waves, but it's just not in a. So this yellow one is in a regime where those gravity waves travel inwards and become just a traveling wave and break. And this is the resonance locking would be more in a regime where these are standing waves. So there are some subtleties with these interpretations. In particular, I can get more into this if you're interested later, but Ma and Fuller think that there might be a regime where this resonance lock can be broken because of that wave breaking of these gravity waves. But there's other studies that suggest that might not be as important. So there's more to explore here, basically.
So the resonance locking, that's about the waves in the star, right? I wonder the other mechanism, are you talking about the tides in the planet or in the star?
All of these are the dissipation inside the star. Yeah.
So the pressure modes don't play any role, the acoustic modes.
I don't think so. Yeah.
I can actually comment on
Yeah.
that. I think it gave me a cool argument for this. Pressure modes, the minimum frequency is set by the dynamical frequency of the surface, which is equal to the Keplerian orbital velocity at the surface. Planets must be orbiting slower than that, so it's never a locked pressure.
Okay.
I just learned that like a week ago.
Yeah.
Does the resonance locking theory make a specific prediction about the types of stars that it should apply to? And is your sample compatible with that?
Yeah, so JJ Zanowski had a nice paper recently where he's looking at resonance locking as a way to maybe explain the hot Jupiter stellar obliquity distribution. And there they talk about that cool stars have those frequencies change more over their lifetime relative to hot stars. And so you would expect more tidal sculpting for cool stars from resonance locking. And that's also consistent with what we find in this work, that we find that cool stars seem to show this steady state region in the tidal decay time scale distribution, but hot stars don't.
I guess the crucial thing is that you want the star's frequencies to increase as the star evolves, right?
Yeah.
To make everything faster.
Yeah.
And is that generically the case for these main sequence low mass stars
I think
throughout
that,
their lifetimes? Like,
yeah, I mean, I'm not an expert in that, but at least from what I've seen from like Ma and Fuller and from JJ's work that that does seem to be the case, but it's more, but you get more frequency change for the cool stars. Yeah.
Sorry, why did it be increasing?
Well, as time goes on, you want to draw the planet inward. So you want the frequencies to increase even faster.
Right, but I thought these ones not locked at one particular mode, right? Is it?
Or it changes modes, it hops from one mode to
Oh,
another
no,
mode.
sorry, yeah, you're right, yeah. It's for one mode, yeah.
Okay, so. Yeah, there's definitely still more to explore on this study, and I'm happy to talk more about it later, but I wanted to talk a little bit about a different class of planets. Tides are important not just for hot Jupiters, but for other short period planets too. And so I want to talk about this group of planets that we know as polar Neptunes. So I've already mentioned a bit about the stellar obliquities, this angle between the stellar spin vector and the planet's orbital angle momentum vector. And when we start looking at these stellar obliquities of the planet population, it opens up a whole range of interesting problems. In our solar system, this angle is very small, as you would expect for planet formation in a thin disk. This doesn't appear to be the case for many exoplanetary systems, as Josh kind of pioneered this field and showed that many exoplanets can have very large stellar obliquities. It's important to kind of clarify the quantities that observers actually measure. So there are, it's kind of helpful to look at this 3D picture here, where if this is our line of sight to the system, this is the orbital angular momentum vector, this is the stellar spin vector, then the true obliquity psi is this angle here. And the projection of that true obliquity psi onto the plane of the sky is this angle lambda. So with observational methods, we can either measure this lambda here, or we can measure this I, the inclination to the stellar spin vector. But we can't measure the psi angles directly. So in order to do that, they need to combine different methods. So a few years ago, it became possible to do this for a large enough statistical sample of true obliquities to understand the patterns across the population. So in this study from Simon Albrecht and Josh and others, they were able to assemble this sample for a number of planets where they could combine these measurements. Here is what the projected obliquity distribution looks like, as a function of effective temperature. And you can see that the obliquities span nearly the full range from 0 to 180 degrees. But when it's plotted in this space of psi versus the effective temperature, then the planets don't span the full range, but rather group into these distinct parts where there's planets that are consistent with being nearly aligned with the star, and then planets that look to be on nearly polar orbits. So I think this observation is super interesting because, for a long time, theories were trying to explain how to get just any stellar obliquity from 0 to 180. But if there really is a distinct grouping into nearly coplanar and nearly polar, then that changes what theory needs to try to explain. And we now need to understand why there might be a collection of planets on these polar orbits. There's an interesting subset that's a pretty small number of planets right now, but it's growing, which are these polar Neptune-like planets. So these I'm kind of defining these broadly with anything in the regime of 1.5 to 6 Earth radii, or masses between 10 to 50 Earth masses. But apart from having nearly 90-degree stellar obliquities, these also have some other interesting things in common. So some of these have moderately eccentric orbits, like 0.1, 0.2 eccentricities. Some of these also show evidence for atmospheric mass loss. And they also have evidence for distant giant planets, which might, the fact that they have these things in common might kind of be clues to some kind of common formation pathway. So we are working on trying to understand these origins of these polar Neptunes, considering both their orbital and physical evolution of these planets in kind of a holistic picture.
These are polar Neptunes, are they all in similar kind of in the distance from the star? So what are the semi-major axis distribution?
Yeah, they're pretty short period planets. I don't know the semi-major axis distribution explicitly, but periods less than 10 days for sure, yeah. So one project that we recently completed on this was led by Emma Loudon, who's a 5th-year grad student at Yale. And she was looking at whether the observed properties of these polar Neptunes could be consistent with the formation channel via a dynamical inclination resonance, which was initially proposed by Cristobal Petrovich and collaborators in 2020. So in particular, let's consider that we're at this early stage of planet formation and start with an inner Neptune planet, an outer Jupiter-like planet at a few AU, and then a transition protoplanetary disk beyond that. So the motivation for this picture came from observations of so-called transition protoplanetary disks, which are thought to have the inner few AU devoid of gas and dust. So the interactions between these planets and with the disk cause their orbits to precess. And when the disk is still there, the outer planet precesses more rapidly than the inner planet. But after the disk goes away, then the inner planet precesses more rapidly. And so as the disk dissipates, it causes a resonant encounter where the precession rates of the two planets are equal. This resonance encounter causes the inner planet's orbit to tilt to, it can reach all the way to 90 degrees if this dissipation happens slowly enough. So this mechanism then is can be a natural way to generate planets on these polar orbits like we see. But the thing that we were thinking about was that this mechanism occurs in the first few million years, but the polar Neptunes that we see today are billions of years old. And during that time, that there's a lot of tidal evolution that could take place, which might realign the planet's orbit. And so for other close-in planets, we know that there's evidence that stellar tides can realign the planet's orbits. And so if this was the case for these polar Neptunes, then that would cause some tension within early formation picture like disk-driven resonance, since these orbits should have realigned instead of staying polar. So Emma explored this disk-driven resonance mechanism with a focus on whether these planets can maintain these orbits over a long time. And she found that indeed these polar orbits appear to be remarkably stable, that they can maintain these over billions of years and will not move under the influence of tidal evolution. So this is a good thing for a theory like disk-driven resonance, because it means that there's no tension with the primordial excitation, that the polar Neptunes could have attained these orbits very early. But another effect of all this tidal dissipation, so I mentioned that these orbits tend to be a little bit eccentric, and this tidal heating in the planet's interior will lead to heat deposition that can pop up the planet's atmospheres. And so if this is happening for the polar Neptunes, we should be able to see this in their radii. A few years ago, I explored this idea with just 1D interior structure models of a 2-layer planet model. So I was just looking at how much could tides inflate planets in general. So here on the right, I'm showing a collection of simulated planets where on the y-axis, I'm looking at the degree of radius inflation. So the amount how much bigger the planet is with tides relative to what it'd be without tides. And I'm plotting this as a function of the tidal luminosity with respect to the incident stellar power. When this is greater than around 10 to the -5, then you can get really extreme tidal inflation, making planets get up to around twice the size of the size they might otherwise have. And so we've shown in past work that this is a really significant effect and that can explain anomalous features within the short period planet population. But applying this to these polar Neptune planets, if they're undergoing this tidal heating, we should be able to see it manifested in their radii. And I'm working with the second year grad student, Ritika Sethi, to study this tidal inflation of these observed polar Neptunes. Ritika has found tentative evidence that the polar Neptunes appear to be more tidally inflated than Neptune-sized planets on aligned orbits. So this plot is showing a sample of planets with those on misaligned orbits in blue and those on aligned orbits in red. And we see on the y-axis the degree of tidally induced radius inflation, and on the x-axis this ratio of the tidal luminosity with respect to the incident stellar power. So there's a mix of planets throughout here, but overall we can see that there's a tentative trend that the misaligned planets appear to be more often tidally disturbed and inflated than the planets on aligned orbits. So we believe that this might reflect a more kind of not chaotic, but a more violent dynamical history of the misaligned planets, which could give them these eccentric orbits and make them a bit more inflated, puffing up their atmospheres. So these tidal effects, while they don't appear to be strong enough to realign the orbits of the polar Neptunes, they appear to be significant in potentially puffing up their atmospheres. Yeah.
So the eccentricity are comparable between the misaligned and the aligned subsamples? In other words, could this just be eccentricity tides or?
Yeah, I think it is, there is a slight trend for the misaligned planets to have slightly higher eccentricities.
Okay.
So it could be, yeah, just eccentricity tides.
Yes, how do you know that, whether it's eccentricities or misalignment or?
That's a good question. Yeah, we're still trying to sort out.
I mean, it's separately interesting that the eccentricity goes along with this.
Right, yeah, but it's, I think, hard to tell whether that's the sole cause of it right now.
Does L tide include the eccentricity factor in there? Yes, right, because.
Yeah, it does, yeah. Yeah,
So observationally, are the polar Neptunes puffier than non-polar Neptunes, so they tend to have lower densities?
yeah, I mean, it's, so we see it more strongly in this when we're comparing to what we would expect them to be if there were no tides.
Yeah.
But there is a slight radius effect as well. Okay, so I am like right at the hour, so I'm just gonna jump now to my conclusions. I was gonna talk a little bit about how we could test tides with JWST, but I wanna just conclude by saying that I think these short period planets are really interesting because they're in this regime that we just don't have in our solar system. And so they display a lot of these extreme dynamical phenomena that we can get a better handle on. So tides are really significant for these planets, and I think they can explain a lot of interesting features. And we're still in the middle of trying to test all of these and get a kind of holistic picture between the orbits and the interior properties of planets as well. So thanks for your attention. I'll take any more questions you might have.
Sorry.
Yeah, I was just wondering, what is the, if you could actually show us the when major punchline for your JWST. You have talked about.
Yeah. So yeah, Josh and I just worked on this perspective review article, which is going to be coming out as part of a PNAS special feature on exoplanets in the JWST era. And we were looking at different dynamical phenomena of exoplanets that might not have been very accessible with previous observations, but could be now given the very high precision that JWST offers. We were looking at a range of different things like planetary oblateness, rings, moons, and so on. But as far as tides, the very high photometric precision of JWST might allow us to detect tidal distortion. So, because the planet gets distorted on very short period orbits, the transit does not look exactly like what you'd expect for a spherical planet transit. And you can see, if you look at the transit light curve of a distorted planet, minus that of what you would expect for like a best fit spherical planet transit model, there's these slight perturbations at ingress and egress that are sensitive to this amount of deformation. And if this could be measured, this particular example here is a very small, just 10 ppm signal. But if this might be measurable, then you could constrain properties like the love number of the planet, which is a handle on its interior structure. And yeah, we also thought about effects of tidal heating on the atmospheric spectra. So tides really inflate the deep interiors of planets, which throws the atmosphere out of chemical equilibrium. And so the abundances of certain species like methane become much different than what you'd expect from a chemical equilibrium model. And this could be, this has been detected already with JWST, and I think it's a really nice like thermometer of the deep interior of planets that could test tides further.
This could vary though, is that there may be variability for this.
Like like this from different epochs if you observe. Yeah, maybe, yeah.
Could you go back to the plot of temperature versus like where you showed polar Neptune's temperature? Yeah, I'm just curious, why does it seem that polar Neptunes are perhaps preferentially around polar stars?
Yeah, I'm not sure. It might just be small sample effect right now. Or it might just be that those are the ones that for which we've been able to observe the Rosser-McLaughlin effect, because smaller stars that will have like higher amplitude signals. Or I'm not sure. I don't know. Maybe Josh. I don't know.
I don't know, I'm not sure, it doesn't look like they're really you're saying that Neptunes are shifted to the left in this diagram relative to the bulk of the objects. You're between 5,000 and 6,000, I guess so, but there's just a couple of objects, if you got rid of GJ 436 and GJ 3470, that's, they would be basically the same, so I'm not sure.
It seems there's no high temperature host system for the low of the ones, right? It's the elevation.
That is the case, that when you get above say 6,500, you don't see a big clustering of low liquid planets.
Right, do we have explanation or this is selection?
Well, the 6,500 does represent the rotational discontinuity in stellar evolution. Above that, stars have different interior structure, different rotational history, tidal dissipation. So it's possible that the cooler stars have stronger tidal dissipation, causing them to lower the.
But somehow still the polar things can.
Yeah, I mean, at least for this regime of polar Neptunes, they seem to be able to maintain those orbits for a long time.
Does that depend on the mass, or would a polar hot Jupiter also be okay?
That is a good question. I think I don't actually know. I don't have a good answer. I know the polar state is like a stable equilibrium, but I think the hot Jupiters would be massive enough to tidally realign. So yeah.
So we are passing 12. So probably we end here, and if you want, we can join lunch together and continue the discussion. Sarah will be here until 3 p.m. 4
Yeah,
p.m.
I gotta.
Okay, and then
Yeah.
she have to leave by train. Okay, let's start again.